Alright, so today I wanted to record a very quick video about modifying the OpenFOAM solver and understanding how we can modify the case and the solver based on our problem definition. So far, I have recorded a couple of videos on OpenFOAM. If you haven't watched them already, I would highly recommend that you pause this video and watch those first, because this is a continuation of my previous video. I want to talk about a simple addition of heat transfer to the icoFoam case. So today what I want to do is the icoFoam solver. I want to add just a simple temperature field to it and make a simple icoT foam solver. That is the sole purpose of this video. So if you are new to OpenFOAM, if you want to understand how to modify solver, this video is for you. If you look at a simple case of forced convection heat transfer, if we talk about the governing equation and I assume 2D case, alright, I would write something like this, wherein I have the unsteady term in the momentum equation, then we have the convection term, the pressure term, diffusion term, and we have an energy equation, which, and since I again assume it to be an incompressible solver, so I then take the liberty of writing something like this, and here we would have alpha nebula square T. So if you look at the icoFoam solver, we already have these two equations embedded in it. Now it's all about adding this third equation. So the sole purpose of this video, as I've already informed, is to modify or understand how to modify the OpenFOAM solver. And in this case, we will be simply modeling the forced convection heat transfer by using this simple equation. Let me talk about the problem definition. So the problem is of a simple lead driven cavity in which we have an obstacle. Now this time what we are going to do is we are going to heat this obstacle to a relatively higher temperature. We assume, say this is at 310 degrees Celsius or degree Kelvin, my bad, and say this is at 300. All the others are insulated, and let's see what happens. It's a very simple or very ideal case and would be rather very interesting to see. If we talk about the velocity boundary condition, they are pretty straightforward. The top lid is moving, and this we have already solved. So what I do is I take the liberty of using the same case as of the previous problem, and then also I'll copy the code from the OpenFOAM library, and then let's get going. So the solver, for getting that, I'm using the OpenFOAM 2406 version of ESI variant. So my case would be located in user lib OpenFOAM and so on. So I'll go to applications, I'll go to solvers, I'll go to incompressible, and then I'll go to icoFoam. Here I simply copy this, I'll copy it here, and I will rename this as, say, code. Alright, and I have the case from the previous simulation. Alright, so, and let me quickly open it and show it to you. If you have watched my previous video, you will understand that in fact this is the case where we had looked at generating the non-uniform mesh in OpenFOAM, and this particular case was all about that. I will link this in the comments, in the pinned comment, the link to the case file, so you can download and modify it along with this tutorial, so that you also understand how to do it side by side with me, so that becomes very easy to follow. Now let us directly get to the code modification. So if we look at the code, a typical OpenFOAM code has these three elements. We have the main .c file, which is going to be the main file, right, main code file, and we are going to have headers and the make folder, which has the rules or the libraries that are required, or the location of the libraries that are required for a particular code, and the rule of compiling and where to store the compiled output. All these things are going to be there in the make folder. So this is going to be the typical construction of any OpenFOAM code. You can check for yourself. Now whenever we write our own code, all right, we will write it in a single file. Suppose the code spans hundreds of lines. Troubleshooting, or rather debugging, becomes very tedious. So what we do is we split these codes into small snippets and then declare them as headers and include it in the main code. So that way all things are properly segregated and it becomes relatively easy to manage. icoFoam is a pretty straightforward solver, so you are looking at only two files. That is not going to be the case most often in OpenFOAM, and you will find multiple header files. But since the case is simple, we have only two files. Let us talk about it. A typical OpenFOAM could should look something like this. The first line talks about including the fvcft header file, which is in fact the finite volume library of OpenFOAM, where it's the heart of the OpenFOAM setup. We'll include this so as to include the finite volume discretization schemes, solvers, etc, etc. So we will include this. Then we'll include the piezo control so as to incorporate the piezo algorithm for pressure correction in our code. And then there are a few other things. I will not get into this because I have already talked about it in my previous videos, and there are a bunch of tutorials online as well. So the idea is very simple, that whatever the things that are required for, say, creating time, creating mesh, declaring fields and all those things, we include it. Even for, say, post processing, we need some header files, we'll include it here from the library. So these are the things that are going to be highly essential for the code to run. If you may look at it this way. For now we don't touch it at all. We move down and we see we have our momentum equation here. So let us compare it term by term. What does it mean? If you look at the first term, or now if you look at this equation over here and the code snippet, things become really easy. So the first term says FVM DDTU. This is nothing but the time term. The second term says FVM DIV phi u. This is nothing but the divergence term. Here this velocity has been coupled with the phase, and ergo this is referred to therefore as phi or flux, and we are just taking the divergence of phi and u together, and hence FVM div phi u. All right, and minus nabla p, this comes in the form of the momentum predictor loop, and the last term over here is the Laplacian term, obviously given by the Laplacian solver, or rather the Laplacian term over here. So this is very self-explanatory. The language used in OpenFOAM library is very user friendly. So if you connect the dots, you can see the pattern emerge. Then we have the piezo loop. We again don't touch anything here. Now once we have calculated, or rather predicted, the velocity, then corrected the same, we can then calculate or incorporate the temperature field. Now you should understand that in the case of forced convection, there is going to be a one-way coupling between the velocity and temperature. What does that mean? It means that first we are going to calculate the velocity, and based on that velocity we are going to calculate the temperature. The velocity does not take any feedback from the temperature equation. There is no such term here, as you can see, but in fact there is a velocity term in the energy equation that we have incorporated. So yes, the temperature equation is talking to the velocity or the momentum equation, but the momentum equation is not talking to the temperature equation, in turn that it's not deriving any information. Say we study the case of natural convection or even mixed convection for that matter, we would incorporate a source term like GB and delta T, wherein we have T minus T ref. So now the T in this source term would be derived from here or incorporated from here, and thereafter they talk to each other, they are interdependent. So that's a very different case. We'll look at it in the future, but not today. We are today going to only focus on forced convection. Hence, after I'm done calculating or correcting the velocity, you can check this bracket ends over here. So after this happens, I will incorporate the energy equation. For that, what I do, I take the liberty of simply copying this over here, and I will now modify this. So I'll name this U equation to T equation. Instead of vector, I'll name it as scalar, obviously because temperature is scalar. Now the first term we have FVM ddt T. Then similarly we have here T, and here we have T. Now instead of nu we have alpha, and immediately when we do these changes, what I do, I will make the notes of whatever changes I have done. I have introduced T equation, and I have introduced, and through T equation I have introduced T, and I have introduced the alpha parameter. So I have to now declare this somewhere. I will also have to tell OpenFOAM to solve this. So I'll write T equation dot solve, right? And that way OpenFOAM will understand that okay, this is the temperature equation. When it executes this, comes to this line, it will realize that we are asking it to solve, and then it will solve it and therefore calculate the temperature values at various control volume that we have used to discretize the domain. So once we are done with this, we have two tasks in hand. One to define temperature, another to define alpha. Where do we do that? We don't see any option here. Hold on. There is in fact an option which is the create fields. So now if you look or have a look at create fields, so here, as the name suggests, we create different fields that are highly necessary for our code to function. So remember, I have two tasks to complete. One is to define T, another alpha. So I see that here the field of pressure has been defined, the velocity field has been defined. So similarly, I define the temperature field. Now since temperature is scalar, I copy the pressure and simply change P to T, because that is what it is. Temperature is a scalar, so I'll declare this. Now one task is done. Now alpha remains. So alpha is a constant. It's going to be included in transport properties over here, just like the viscosity is defined. So what I do, I simply copy this, because obviously alpha also will eventually have similar units. So I say this is alpha and will be read as alpha. Dimension can be same as viscosity and will be read from the transport properties file of the case. Again, if you are wondering about all these things, how to modify the case, I've already prepared the video. Please go and watch it. If you are confused, now is the good time to do that. So I'll close this because I've done editing, and I think no more editing is required. Let me check very quickly. In icoFoam, I did add the temperature equation. I asked it to solve it. Yes, that's it. Apart from that, in the create fields, I went ahead and defined the alpha, and then having also introduced the temperature field. There are no more tasks to do. This is also done, but there remains one more task, or one question pops up in my head, that how does the OpenFOAM library know that I have modified the code? And also, what about the compilation? So these two questions pop up in my head. Let's answer them one by one. So the first thing that we can do, or we should do, is rename this file to a new name. So icoFoam, icoTFoam maybe. Alright, and let us go to main and let us see what's happening in these two files. So if we have a look at these two files, the options file has the link to the respective library location. So we don't touch it because obviously we haven't changed anything there. But in the files file, we do see that there are two lines which talk about the file that is supposed to be executed. I will change it to icoTFoam, and where is the executed, or rather the executable file is going to be stored. This talks about that. So what I do is I modify this and change it to user app bin. Let me quickly show you what I mean by this. So say for instance, if you navigate to this location, foam app bin, and you see here all the OpenFOAM library executables are stored, right? And if you go to say foam user and app bin, and here if you see here all the user compiled files have been stored, so that we have that segregation right from the start. So I'll change it to user app bin, where icoTFoam would be stored. It is that simple. Now, one common mistake that people usually do is that they fail to either change the name of this or this, and they eventually land up in trouble, because then the library gets confused between your icoFoam and the library's icoFoam, and you may be seeing that the code is not running properly and all those things. So be very careful when you do these things. So yes, now the OpenFOAM library knows that which code to compile, and the compilation now I have to do. So let me quickly go ahead and do that. For doing the compilation, I'll open a terminal at this location, and I will run wclean and wmake. So when I do that, the OpenFOAM code compiles. It will take some time. Now let us see what tasks we are supposed to do in the case modification, right? So if we talk about the case, now see, in the code we have introduced a new field, which is what? Which is T. So in 0 folder I should add T. That is the first task. Second is that in the transport properties, all right, in the transport properties I should add what? Alpha. Then if we talk about the system folder, in system folder, what are the files that I need to change? I would have to change or add the FV schemes file, and I will have to change the FV solvers. I will have to do that. Apart from this, no other changes I think I would have to do. One more thing probably, which I think I'll have to check. If you recall, the problem is that we have an obstacle inside a cavity. The top lid is moving, and we are deciding to make this hot. For that to happen, I will have to define that boundary. So let me check if my block mesh file is correctly defined. If not, I'll have to first modify my block mesh file. And if I modify my block mesh file, I will have to in turn go ahead and modify U and P too. So these are the things that I need to do. I prepare a checklist, I go to the case, I open block mesh and I check the file. Yes, in fact, what I've done is I had compiled everything in under the fixed walls. I will have to separate this internal cavity. I will have to create a separate patch for it. Let me do that. Here I call it say hot block and I replace this. So what happens now, let me quickly show you. By running the block mesh command, I open parafoam and here I show you in the patches the hot block. So if I only plot the hot block, so this is what it is. And if I plot say the fixed walls, these are the fixed walls. The moving wall if I plot, and these are the moving walls. So yes, now it has been correctly defined. Alright, now that task has been done. What? Modification of the block mesh file. Moving on, I'll have to first then modify the 0. So I go to 0. I think I had included this before. Ideally you should have these two files. Alright, ideally you should have these two files. So we should have pressure and velocity. What I'll do is I'll copy the pressure, rename it as T, and now I open all three of them and I'll start to modify. So this is the file T, so I'll change P to T because this is a wall scalar field that stays. The dimension has to be changed, so I'll have to give the dimensions of temperature, which is going to be here. The location again you can look it up online, it's very simple. Internally, initially I assume everywhere it's 300. We have the moving wall, we have the fixed walls, but apart from this we do have one more patch, which is the hot block. Now moving wall, I assume that it's exposed to the atmosphere, so I assume that it has a constant value. Again, this is an assumption that I decide to make, so I define a constant value there of 300. Fixed walls, I assume they are insulated. Hot block, on the other hand, I will have to give it some higher temperature, so I decide to give a Dirichlet boundary condition of 310 degrees Celsius, relatively higher. Alright, then I go to pressure, I check. Here as well, I will have to modify the boundary condition, include the hot block. Yes, in fact, in the pressure, it will stay 0 gradient, so that stays. And in velocity, what is the situation? In velocity, I will have to define hot block boundary condition there as well. I decide to keep it no slip because it's going to be no slip. It's a patch. If suppose you don't want to give no slip, since you defined it as a patch, you can also give this, doesn't matter. Now once this is done, we close this. So this part is done. Next, transport properties. So we go to transport properties and we check here what's going on. So only new is defined, and that too it's 0.01. So I take the liberty of defining alpha as well. For now I keep it at that value. It's a trial simulation, so it doesn't matter. So transport properties done. Now let me go to the system, right, and let me modify these two files. So if we talk about FV schemes, what are or where should we include the temperature term? It's very simple. There is no gradient of temperature. There is only the Laplacian term and the divergence term. So Laplacian is default. I have kept it as it is. So here as well, what I do is I simply copy this line, change U to T, end of story. Moving on, FE solution. In FE solution, we have the pressure field, we have the velocity field. So I quickly copy this because all the velocity field terms very similar to that we have in the energy equation. So I use the same solver and smoother that we have used for velocity for temperature. I copy that, I rename it, end of the story, moving on. This is done. So in system we have completed FV scheme, FV solver, we are good to go, right? So at this point, let me run block mesh and let me run icoFoam and let me see what happens. So let us run the simulation for a while. Meanwhile, as the simulation runs, you can quickly open paraFoam as the cases, the time steps are written. You can immediately open paraFoam and see what's happening. So let me plot the temperature and play that out. Yes, of course, based on the velocity field, the temperature field is also evolving. If you want to reload the the time steps which have been run later, you can do that. You can adjust the time, the temperature values as well. And here, if you plot the velocity field, you can see how it is still evolving. The simulation has stopped, the 5 seconds have been reached. So yes, we can run longer as well. So if you play this out, it's evolving something like this. And if you play temperature out, it's evolving something like this. For the case of temperature, you can plot the contours as well and see the contours individually. And let me again play it out for you. This is going to evolve in some fashion like this. Obviously the physics and everything is very vague right now. It's not up to the mark. We have not done any steps like code validation, grid dependence. So these are not reliable results, but these are some results that you can then start to work on, polish them, do all these steps, and then probably you will have some meaningful results. But this tutorial was not to get the meaningful results, but just to get some results so that we understand how to modify an OpenFOAM case and code if you want to say model a simple heat transfer problem. Thank you for your time. Have a great day.